All right, I'm going to attempt to explain number 14 that asks us to show that if k is positive constant, the area between the x-axis and one arch of the curve of y equals the sine of kx is always 2 over k. So what in the world are we talking about? The area between the x-axis and one arch of the curve y equals kx. So I'm going to first of all start by looking at Desmos. And what I've done is I have plugged in y equals sine of x, but I've modified it. I put y equals sine of ax so that I can plug in different values of a. And I created a slider down here. A equals 1, 2, 3, 4, and so on. And I'm shading it in so that it's the area we're looking for. Y is greater than 0 and less than sine of ax. And then I've given a domain, x is between 0 and pi over a. The reason I chose pi over a is that one arch of the curve happens from 0 to pi. And when sine goes from 0 to pi, it creates one positive arch. And so if I want to get to pi, and let's say, for example, a is 2, I'm only going to need to go take the x values from x equals 0 up to pi halves, because pi halves times 2 will give me pi, and it'll give me back to 0, and that's going to give you one arch. So that's kind of a important observation at the beginning, is the width of our interval will go from 0 to pi divided by a, or pi divided by k. I could have used k. All right, and then, so what I'm doing then is I'm calculating y down here as the integral from 0 to pi over a, that's the left to right domain, and the curve is sine of ax. And I can look at what the different areas are for these values. And so one way to demonstrate what our solution is going to be is to come back here and think about different values of k, and it says that it's a positive constant. We're going to try and just kind of demonstrate it by saying, I think you mentioned doing several examples. So when k is 1, what's that area? When k is 2, what is that area? So over here, this is our area that we're calculating from that integral. So jumping back to Desmos, when it's 1, we can see that it goes from 0 to pi as the curve, and the integral is 2, the value is 2. So we're going to come in here and say equals 2. Then I'm going to jump back over here, and I'm going to move a to equaling 2. Notice how the value of the area is now only 1. The value that I've got, I've made it half as far to the left, from left to right, and so it's now a size of 1. And so if I come back here, I get 1, or you could think of it as 2 divided by 2. And what you can kind of see and reason out is that I'm keeping the same basic height and shape of my curve, but as I compress it, it's now not half as big, but it's a third as big because I'm compressing it by a factor of 3. And we get 0.6 repeating, or 2/3. And if I come back here a couple more times, right, when it's 4, I get 0.5. Right, 0.5, which is 2/4, and so on. When I get 5, I get 0.4. All right, 0.4, which is 4/10, or 2/5. 2, 2 over 2, 2 over 3, 2 over 4, 2 over 5. Okay, and if we continue on to k, dot, 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 we're going to get 2 over k. So there's a more sophisticated analytical description we can give, but hopefully that's a good enough explanation for you.